How's it going, everyone? Mr. Geyser here with the video for our Lesson A. For Lesson A, we'll be looking at the tangent function. For the tangent function, we have four main skills and learning objectives we'll be conquering. First, we want to try and understand the tangent function while using that unit circle. Two, we want to find the amplitude and period for one cycle of that tangent function. And three, we want to sketch the graphs of the tangent function and describe those transformations. And finally, four, we want to describe the characteristics of that tangent function. For this lesson here, recall that when an angle of measure theta is in standard position and a unit circle is centered at the origin, there is a point P where that terminal ray intersects the circle. The tangent function f theta is equal to tangent theta gives the slope of the terminal ray if it exists. Since the slope of the terminal ray is the ratio of the change in the y values to the change in x values between any 2 points of the ray, the tangent function is also the ratio of the sine function and the cosine function. Notice that the slope values of the terminal ray repeat every 1/2 revolution of the circle. The tangent function has a period of pi. Notice that our period for our sine and cosine is 2 pi, and they only repeat after a full revolution around the unit circle. Tangent's unique, where it repeats twice when it goes around the unit circle one full time. A few quick definitions for a tangent function. Again, that tangent function matches the measure of the angle in that standard position, where it's the ratio of tangent theta is simply equal to sine theta divided by cosine theta, where cosine cannot equal 0. If it does equal 0, that slope does not exist. For our tangent curve, a tangent curve is just the actual graph of a tangent function, while tangent of theta is again the ratio of the change in the y values to the change in the x values between any 2 points of the ray. We can explore this by looking at our examples today. For example 1, the graph of the tangent function will complete one full cycle in the interval of 0 to pi. So the period of y equals tangent theta is pi. However, there is a vertical asymptote at that theta equals pi over 2. On what continuous interval can the entire behavior of the function be shown? In part A, we want to match the table of values for x and y on a y equals tangent x from the unit circle. For this table here, what we want to try and grab is that unit circle that we created from that previous topics. For this unit circle here, we know that each of these degrees correspond to each of these radians, while each of these points P are made up of our sine and our cosine values. So sine of 30 or sine of pi over 6 would equal 1/2 here, while cosine of 30 or cosine of pi over 6 would equal root 3 over 2. We want to use this knowledge to try and find each of these points today. To try and create that ratio, let's take that first example point of that pi over 6. For pi over 6, all we need to plug in is that theta into our sine and our cosine. We already know what these values are on our unit circle. We simply grab them from that unit circle there, and we take 1/2 divided by root 3 over 2. If we were to actually divide this out here, we would get this 1 over root 3 as our answer. This answer here is a good answer, but because it has a radical in the denominator, we want to try and bring that radical from the denominator into the numerator. To do this, it's very simple. We simply have to multiply that term by a value of 1, but a very specific value of 1. We want to multiply it by this radical over itself, so square root 3 over 3. These two 3's here turn into a non-radical 3, so it's just a positive 3 over radical 3. And we can bring that now into our table. Now let's try and explore these two key points that we'll be looking at later in our lesson. The first key point here is going to be that start of a 0, and that second key point here is going to be that end of a 0 here. So we know that at tangent of 0, it's also going to be 0. And at tangent of pi, it's going to be 0. And really, that's just because sine is equal to 0 in those positions. Anything divided, or sorry, 0 divided by anything is just going to give us that value of 0. On the contrary, if we look at that very center point here, where we now have cosine is equal to 0, at that very center at pi over 2, it does not exist. So we know that for this tangent graph, wherever it's going from, we know it can start from that 0 and going up to that pi over 2, but it does not go from 0 all the way to pi. There's a discontinuity at pi over 2. So that interval there is not going to be from 0 to pi. Rather, the interval is going to end at pi over 2 and start on that bottom 270 or 3 pi over 2 degree. Let's continue to explore the rest of this table here. Let's take this back and forth here by solving out that pi over 4 and that 5 pi over 6 at the same time. Really, when we're solving these 2 points at the same time, we're grabbing the same sine and cosine values, but our cosine just happens to be negative. So for that pi over 4, we happen to get that 1, and for 3 pi over 4, we happen to get negative 1. Now let's go one more in. Let's try and find pi over 3 and 2 pi over 3. When we try and find pi over 3 and 2 pi over 3, it's that same exact process. We take that value for sine and divide it by cosine, and we take that value for sine and we divide it by that negative sine, or by the negative cosine, and then we get root 3 for our pi over 3, and then negative root 3 for 2 pi over 3. And notice that pattern. From this does not exist discontinuity, we basically have a positive version of these values and a negative version of these values. So we actually know what this 5 pi over 6 is based off of that pi over 6 value. It's just going to be that negative 3 or root 3 over 3 value here because it's going to follow that negative pattern. Once we found all of these points here, we're now able to move on to part B of this problem here, where we want to state the interval of x where the y values are increasing. For just this table here, I want you to see that the y values for this table here are increasing from 0 all the way up to that does not exist, and it goes from that does not exist to that pi. What I want to see is that from 0 to root 3 over 3 to 1 to root 3, all of these points here increase over time. Same thing from these points. From a does not exist point to negative root 3 over 3, that's an increase. From negative root 3 over 3 to negative 1, that's an increase. From negative root 3 over 3 divided by 3, that's an increase all the way to 0. So it's increasing always. Tangent of x functions are a unique function. Tangent x is increasing from 0 to pi over 2 and pi over 2 to 0. These types of functions that have these types of functions have a unique name. For part C, we want to state the intervals of x where the y values are decreasing. There are nowhere where tangent of x is decreasing. The y values never decrease. The function is known as monotonic. A monotonic function or graph either never decreases or never increases. Our sine of x function, regardless on how we change it, will always be decreasing or always be increasing. In example 3, we want to graph the function y equals negative tangent of x and then state the period and show all asymptotes. In part A, we want to describe the behavior of the graph when a is less than 0. First, just to display what it looks like, I want to show what that tangent of x looks like here. And whenever we have a negative tangent of x, it is going to be the same kind of reflection as our sine and cosine. Whenever a is negative, it's going to be a reflection across that y-axis. It once was in this shaded region here, and we reflected it across that y-axis. For this problem, we want to describe that the period is still equal to 1 pi. And if a is equal to negative 1, it causes the parent function of tangent of x to be reflected across the y-axis. Tangent of x is known as a monotonic function that is always increasing. Or, for negative tangent of x, it's a monotonic function that is always decreasing. And as a reminder, those monotonic functions are just functions that do not change from increasing to decreasing. They just stay increasing or they just stay decreasing. We now want to take a look at the parts of our tangent function here. When we're graphing variations of this tangent function, we want to first look at our amplitude and the b value. We want to find the 5 key features. First, we want to find 2 consecutive asymptotes by setting the argument equal to the parent function asymptote. What we mean to say is that these arguments inside of our child functions, these b times x minus c, if we set them equal to this here, negative pi over 2, the asymptote equation for our parent function, we will then be able to find the left-bound asymptote for that child function. It's a very unique equation for tangent of x. In part 2, we want to identify an x-intercept, the midway between those two consecutive asymptotes. We just find in between these two here, and that is going to be where our x value is, but the midline will determine what the y value is of that origin point. For 3, we want to find the points on the graph that is 1/4 and 3/4 of the way between those consecutive asymptotes, and those points will correspond to the negative a and the positive a from this center point here. What we want to showcase is that this here, the top point, is going to be the positive amplitude. This down here will be the negative amplitude. The x value here is just 1/4 of the way between our two asymptotes, or really 1/2 of the way between this intercept point and one of the asymptotes. The fourth and final step is to add any additional cycles to the left or right as needed. For these for the key properties of our tangent function here, we want to try and use these kind of equations to describe the domain. These here will allow us to describe the domain for any tangent function. We place the b value of the tangent and the c value of the tangent, and then solve for x. Wherever we solve for x, it's going to be an exclusive domain. So you're going to get an answer that looks like x does not equal something. Our range for tangent should always be negative infinity to positive infinity. It is very rare, if ever, we will have a range that is different than this. It's really difficult for us to think of a tangent function that wouldn't have this here. The only thing that I can really rationalize is if the tangent function was completely rotated 90 degrees, where then the domain would be positive to negative infinity. But really, for all of our tangent of x's, range will be negative infinity to positive infinity. These a values here are still going to be known as our amplitudes, and this is going to cause the vertical stretch factor. Our period has a new equation. It's no longer that 2 pi over b, for tangent has a single pi period, so we'll use this equation of pi divided by b. Finally, those 5 key points we want to use for tangent functions is that vertical asymptote, that negative a value, intercept, positive a value, and then that final asymptote. Let's put these key properties into practice with their final example. In example 4, we want to use transformations, graph each function, state the period, and show all asymptotes. We're going to find the a and b value for part A and part B at the same time, state those 5 key points for both equations, and then one at a time we'll graph A and then we'll graph B. First, let's just find those amplitudes for both of these problems here, and we know they're just going to be that front leading term in front of that tangent. So in B, it's going to be a positive one, and then for A, it's just that negative one. They're both invisible ones right here. For those B values, these B values are going to be used to help us identify what that period is. This B value here is just that coefficient in front of x, pi over 4, while the B value here is just that denominator, but really it's just going to be 1 over 2. Now for tangent of x has a different period function than cosine and sine. We do not want to use this equation here for tangent of x. It's just used for sine and cosine. Rather, we want to use this tangent period equation. We simply divide pi by b, not 2 pi. For part B, we were able to find the period is 4. For part A here, we were able to find that the period was 2. Now we want to try and state the key points for a positive amplitude versus a negative amplitude. For this negative amplitude over here, our approach for this graph starts in the positive direction and then goes down to the negative direction. So we start at that asymptote, but the second point, the y value, will have a positive amplitude, while the fourth point is going to have a negative amplitude as its y value. That third point still that intercept, and that last point still that asymptote. For any for any child function that's positive a, like the parent function, we still use those 5 traditional key points. One's from tangent of x here, where we have the asymptote and we approach from the negative direction, so we have a negative amplitude for our y value for that second point, hit that intercept, and then go up in the positive direction. So that fourth point will have a positive a in its y, and then approach that second asymptote towards positive infinity. Let's graph part A now, where we first want to plot that origin point. This origin point here will always be 0, 0 if and only if there isn't like a C value. As long as we don't have a phase shift, our first point is going to be that 0, 0, and then those next points are just based off of the period. We can do one positive period point and then one negative period point for this first graph. Once we have those period points, we now want to split them right in half to find where those vertical asymptotes occur. And really, we can either find it by doing period divided by 2 and then finding what that x value is, or we just find what the middle point is between these two and then just draw a dotted line between that. We can also use that little split technique again for that next key point. That next key point occurs right in between that first asymptote and the intercept. We find that midway point between those two, but really they're just going to be a pi divided by 4. And then the y value is that positive a. So the actual second point for part A is going to be this x value of -2 or negative pi over 2 and positive 1. We can do the same thing for this fourth period here, or this fourth point here. We find that in between, that halfway between the intercept and that last vertical asymptote, that's going to give us that x value here of pi over 2, and then we just grab that negative amplitude of -1. Once we have those 5 key points, we now just connect those dots and we approach from that positive to that first point and then go down to the negative passing through these points. For part B, we would like to break it down into 3 main steps. The very first thing you want to do with graphing any kind of function is just identify where your origin point is and where that next point occurs. That next point occurs based off of a period. You can go in that positive or that negative direction. Step 2, split your graph in half to identify where those vertical asymptotes occur. Step 3, split your halves again into fourths now. Once you have these fourths, you want to keep in your head or mark on your y-axis the positive amplitude and the negative amplitude. These fourths of a period, positive amplitude and negative amplitude, tell you where these other 2 points occur based on your tangent function. Remember, if a is negative, it is less than 0. We're going to do graphs like part A where we don't approach from the negative, we approach from the positive. Keep this in mind. It's going to be based off your a value if you're approaching from the negative or approaching from the positive. Once we have those 3 key points, let me just get rid of all that nonsense there, we're now able to fully graph our part B. For today, we explored our tangent function, broke down its elements for amplitude and period, and learned how to take a child function and then graph it on a coordinate grid. Thank you very much for joining me. If you have any questions about our examples today, please leave them in the comments down below. I look forward to seeing all of you guys in class. Take care.